can
Oh,
share your screen also in the meantime. So, very good morning to everyone present here. So today is the third day of our online short-term course on computational methods and analysis for engineers, organized by Department of Chemical Engineering, NIT Jalandhar. So I am the course coordinator, Dr. Rajkumar Arya, Associate Professor. Welcome you all to this short-term course. And the convener of the course is Dr. Anurag Kumar Tiwari. And patron and head of the department is Dr. Changita Gar. So speaker for today's first session is uh, Dr. Sharad Bhartiya, professor at Department of Chemical Engineering at IIT Bombay. So let me introduce Dr. Sharad Bhartiya to all the participants present here. Uh, we have amidst us Dr. Sharad Bhartiya, who is a professor at the Department of Chemical Engineering, IIT Bombay. He is currently serving as the head computer center at IIT Bombay. Dr. Bhartiya has an excellent academic record, having completed his PhD in chemical engineering from Oklahoma State University, USA. Prior to that, he completed his MTech from IIT Madras. Earlier, he completed his Bachelor of Engineering from Regional Engineering College, Durgapur. Prior to joining to IIT Bombay, Dr. Bhartiya worked as Dean, Academic and Administration at IIT Goa. He was a research associate at the University of Delaware, Newark, DE. He was also associated with the Bhabha Atomic Research Center, Bombay, as a scientific officer, and Galaxy Organics Private the Limited, Tarapur, as a process engineer. Dr. Bhartiya has 2 patents granted in his name, wrote 1 book chapter, and has 8 recent reviewed journal papers to his credit. Dr. Bhartiya has guided 20 PhD students and 43 MTech students. He is the member, Governing Council, Ram Rao Adik Institute of Technology, Navi Mumbai, member of NOC, Computer Applications in Biotechnology, CAB 2013, Mumbai, member NOC Dynamics and Control of Process System, DYCOPS 2013, Mumbai, member IPC Control System 2012, New Orleans, a member IPC Control Systems 2010, Stockholm, visiting faculty at the University of Leon. Dr. Bhartiya received the Amar Dai Chemical Award for the research by the Young Scientist in the year 2004 and was the recipient of General Aptitude Test for Engineers Scholarship awarded by Government of India for the year 1991 to 1993. So with this short introductions, now I would like to Professor Sharad Bhartiya to conduct the session. Over to you, sir.
okay. Thank you, Rajkumar. I hope everyone can hear me.
Yes, sir. Yes,
I'm
sir.
I'm
Yes,
not
sir.
sure who Rajkumar was talking about. It was not me. It was somebody else, Rajkumar. But thank you for your introduction, and welcome everybody. This is the third day of this short-term course, and I think Professor Tiwari, Professor Rajkumar Arya have done an excellent job of organizing this, and I'm very happy to be here and to be able to talk to you a little bit about a topic which is on machine learning. So let me start presenting my uh, screen, and you should be. I I hope you are able to see my screen now. And in interest of lower bandwidth, I will just turn off my. Can somebody confirm that my screen is being shared now?
Not yet, sir. So it may be visible. It takes time actually sometimes.
Okay. Okay. So I will, maybe just start while it comes up by saying that I'm delighted to be here. I'll talk to you about some topics in machine learning. And this topic of machine learning has taken parts of academia by storm. It hasn't really been completely, what should I say, uh, very successful in chemical engineering, at least in the earlier attempts, but more so it is now taking roots, and there's a lot of activity that has started in this area. So, it's very difficult to give a complete overview in a 2-hour lecture, along with applications in chemical engineering. I always like to think of keeping ourselves grounded in terms of searching what are the topics for us as chemical engineers. And but machine learning is agnostic to the discipline, and it can be applied, as you know, very famously in image processing and a lot of other things. So the real explosion in research in machine learning, or I won't say research, but activities in machine learning, happened with there was this AlphaGo software, and Go is a game, is a Chinese checker kind of a game, and there was this machine learning based on reinforcement learning, which could defeat the world champion consistently. Okay, and then it became clear that here was, you told the rules of the game, and an algorithm kept on learning, and after enough times it could actually defeat world champion consistently. So from that point forward, I think, again, a lot of interest restarted in machine learning. Um, so the idea in ANN is not new. I mean, it was way back in end of World War II, when Rosenblatt, and 1960s when Rosenblatt and others started with a perceptron. In 1970s, and the idea was that it mimics the human way of thinking. But in 1970s, there was a book published by Minsky and Papert, which showed that, although it can do so many things, including echo cancellation in communication, but it can't solve a very simple problem. And let me see if I don't think I'll be able to. Oh, I can write on it. So, the problem that Minsky and Papert.
Excuse me, sir.
Yes.
Okay. Can you share your presentation, because
Yes.
you have to go to the presentation slide actually.
Is my presentation slide not visible?
It was coming earlier, then it suddenly went off actually.
Oh, I see. Yeah, this could. So how can I share it? Can I email it to you?
Just you can do that also.
Um,
So I can share from here, and you can talk from there. You can give the voiceover from
oh,
their side.
that's
That can also be done.
yeah. It is showing now. It is not presenting. It got turned off, it looks like. So let me
So
first start the presentation, then I'll go
reshare
to my
again
email,
actually.
and it's visible.
Mm, uh,
Let me
not yet.
just
Yeah, it
email
will
you
come.
my talk as well. So if that happens, no,
Yeah,
Rajkumar, you
that's
can just
happened. Yeah, no problem. So, actually, this is technical things, and yeah, it's coming, but it's just actually blank thing actually.
okay. So I am just now trying to mail you. My words are slightly big. file. Are you able to see my screen?
Yeah, I can see, but it's coming only your name as and presenting. That's all. Actually, content is not visible.
Hmm. Okay. Um, it's an 8 MB file, so I was. It's, yeah, that must be because of
Yeah, there's
connection.
something. Yeah. So in the meantime, you can give them this idea actually. So we will keep on talking on that way.
Yeah. So yes. So so essentially, as I was saying, that there was a very simple problem called exclusive OR problem. It's a classification problem, and so there are two categories. So if you want to, your exclusive OR is essentially 0, 0, and 1, 1 is an AND, is 1. Okay, it's positive, and 0, 1, 1, 0 is negative. So there are two categories, and in the two categories, uh, yeah. So Rajkumar, let me also turn off my camera because that
Yeah, sure. No
eats
problem.
into my bandwidth. Maybe
Yeah.
I. Yeah. So essentially, when so they were saying that 0, 0 and a 1, 1 is a positive category. So if it is not, it is AND, and if it is positive, positive, it is also a positive. But positive, negative, or negative, positive is a negative. So that's an exclusive OR kind of a situation. And in that situation, it was that if you can see my screen, no, you just let me know. So I will take off
Yeah,
from there. Okay.
sure.
So in it's a simple classification problem, and that simple classification problem could not be solved by a perceptron neural network, and that is what killed the funding and interest in machine learning in 1970s till 1980s, when there was a neural network which was known as a backpropagation neural network or a multi-layer perceptron, which again fueled interest in machine learning. And from that point forward, it has been a very, very successful run, so much so that a large number of problems are being solved today. Large number of practical problems are being solved using machine learning. So, so Rajkumar, it is still not visible.
Yeah, it's coming only your name. Yeah. It came just now actually.
Name means
Uh,
my screen is not showing.
uh,
Is,
it's still. It came just now for a few seconds and then turned it off. So it's visible now, sir.
okay. I
It's
hope it
visible, sir.
stays like the second run of machine learning. Yeah, I hope this also stays. So, so let me start off by saying what a yeah, what a neural network does. So essentially, there are two problems that you can solve using machine learning, and I'm talking about specifically. I'll talk entirely about neural networks. So from a math point of view, a neural network is essentially part of estimation theory, learning, okay, or fitting. So a lot of people ask me, so is neural network essentially curve fitting? So yes, a part of neural network is regression. Okay, so that is one broad activity that it can do. And as you can see from the figure on the top, that this regression it's able to solve. So given these data points as shown over here, you can actually solve. You can fit a curve, and the curve can be highly non-linear. Okay, like shown on the right hand side. And another major application of a neural network is classification or labeling.
Sir,
So when
excuse me, sir.
yeah,
Uh,
Yes.
Are you sharing as a
Yeah.
mean the window or your PowerPoint window? Can you click on your
I have
PowerPoint
opened my
side
PowerPoint window.
and then you have to say,
Yeah.
now it's visible actually. So try to be here only. So now it's visible.
Oh, shall I make
Uh,
it full screen? Shall I make
yeah,
it full
yeah,
screen
yes, sir.
like
Yes,
this?
sir. Yes, sir.
Okay, maybe that will help.
So it's
So
visible
as
now.
I was saying,
Hmm.
that either it solves this regression problem, okay, or it solves the classification problem. So in a regression problem, as you can see on the top, that these targets are continuous. Okay. So it is like, you want to predict viscosity as a function of temperature, or you want some ideal, some uh, equation of state, okay, which is complex, and you can solve such kind of a problem. So given the change in volume and temperature, you want to be able to predict what is the pressure, for example. Now that's continuous. Slight change in inputs, slight change in outputs. Okay, that's continuous. Additionally, you can solve classification problems or labeling problems. So labeling problems are like given below. So you can see the pluses, which are blue, and you can see the gray squares which are filled in with gray, and you can see that there are two labels. For example, you can say that the process is normal and the process is not normal. Okay, so here it is not that a small change in input causes a small change in output. In fact, a small change in input would still mean that the process is normal. So these are discrete. The targets or the outputs are discrete. Okay, so you can say a 0 is for normal and 1 is for non-normal. Okay, so in the bottom there are some finer nuances. One is you can see that these pluses and the squares are linearly separable, which means if you draw a straight line, a linear line, you can actually separate them into two regions. Okay, and this red line is known as the decision boundary. On the extreme right, you will see it says inseparable, and you can see that you cannot draw a decision boundary. Okay, if means you cannot draw a linear line which will exactly separate them out. So in the middle, it is non-linear, separable but non-linear. So you could actually draw a decision bound, not a linear decision boundary, but a non-linear decision boundary, and try to separate out the pluses and the squares. Okay, so this is it is non-linear but separable. On the right hand side, one could argue that if you were a very good kind of an artist, you could have drawn, I don't know if you can see my drawing. See, I'm trying to draw one. I don't know if I would succeed in drawing some boundary and weave through all these pluses, so that finally I have all the pluses together. Okay, and maybe I can still, no, I have not. There's one plus is remained inside. So you could have done something like this. So what ANNs allow you to do, no, is draw these really complex decision boundaries. And you can separate, which are not linearly separable, but you can separate them by use of these hidden layers. Okay, and I will come to that in some more detail. So let me skip this in interest of time. I'll just tell you briefly, this is only for historical purpose, that what is neural in a neural network. So you know that, when you have two neurons in the brain, so there is this massive parallel processing that takes place, that information which goes into, through these dendrites, the information gets communicated to an uh, to this central processing unit of the neuron. Okay, so you can see that there is so much information here. I can call this input x1, x2, xn, and so on. All these inputs come into the CPU of the brain, of the neuron, and it gets processed, and something is communicated through an axon, and this input then goes to the next neuron. In this is connected to the dendrite of the next neuron through what they call a synaptic junction, and the synaptic junction essentially weighs this. So it tells how important is this. So if I it basically tries to calculate some kind of a net. I'll call it net over here. So all the inputs that you see are connected to a net, and then there is an activation function, which I'll call it as F. And this F decides what is the output of this neuron. Okay, and we'll call that a Y. And this Y becomes an input to the next neuron. Okay, now just like shown over here, that each input or each output of a neuron is connected through a synapse to the next neuron. This synapse actually does the weighting, so it multiplies the input with a W. So these inputs over here were also multiplied by their corresponding synaptic weights. Okay, and so you have this W1x1, W2x2, Wn(xn), and so your net n is nothing but the summation of Wi xi, and the thresholding, which is whether the neuron fires, as they say, is basically f of n. Okay, so that sum, let me write it here again. This is equal to y. That y then goes to the next neuron. Okay, so let's formalize it a little bit. So it should be clear to you that you have neuron 1, you have neuron 2. Okay, this is the output of neuron 1. This is the output of neuron 2. Okay, so this is N2, W2X, and we being engineers always add a bias term. We say, okay, if you just do WX, it will pass to the origin. Let me put 1 plus Y intercept. Okay, so we just make it a bias term. So W's are the weights and B's are the bias. Okay, so that is the output of a neuron. So you can see over here that you had, I've gone back to my previous slide, that you had W1x1, W2x2, Wn(xn). These were actually outputs of other neurons, and they get netted, means the summation is taken over here, and the activation function F is applied to them. And then they go inputs to the other neurons. Okay, so that's the, yeah.
Excuse me, sir. Actually, in case of the now we can see the window actually. So maybe you can click on share the entire screen.
I think I should not.
So entire screen means your whiteboard and everything would come in that case. So I can see this window, this slide now. So where you wrote F1, neuron 1, neuron 2. Yeah. It was not visible previously actually.
Yeah, actually, I think it's because of the connection.
Yeah,
see,
yeah,
when I'm changing the slides, so I should not change slides very often. So yeah, I will keep that in mind.
Yeah.
So I'm sharing the entire screen. I have made it full screen now.
Yeah, that would be much more better. So, everything on the screen will come.
Yeah. Yeah. So now you can, so let's move forward. Okay. I'll just tell you now what this processing unit looks like algebraically. And you'll see that it's a very, very simple, each neuron is a very simple unit. If you can see this slide, which says ANN background, simple input, single output, a single input, single output neuron, you can see that the input I have shown here is P. Okay, previously, so the common names used for input for an engineer is X. For a person working in neural networks, we may call it P because he says it's a prototype. And output is Y or an A, as shown over here. So what is your output? Your output, the net N, is essentially W times P plus B. B is the bias. So bias you can think of as an input 1, which is getting weighted with the weight B. Okay. So N is equal to WP plus B. So I will write over here N is equal to WP plus B for a single input, because there was only one input P. If there were more than one input, it would be P1, P2, P3, and so on. So that's not a limitation. It can take multiple inputs. Just like you saw in the neuron, that one neuron can be connected to many other neurons. Okay. And the output is then thresholded through this F, which is known as the activation function or the thresholding function. And the output is coming out of that activation function is A. Okay. So A is equal to the F of WP plus B. So it's very simple. If W had the value of 2, if the synaptic weight was 2, the input was 3, and the bias was -1, then WP plus B is essentially 5. and then you take a thresholding function of 5. And what are these thresholding functions I'll come to, which are shown in my next slide, which I'm sharing right now. So in this case, you can see that you could either have the thresholding function to be a pure linear thresholding function, okay? You could also have it to be a logistic sigmoid function, a logistic or a log sig as we call it, okay? Or there could be a transfer function which is a hard limit. So it is 0. If the net is 0, it gives the neuron does not fire. If the net is greater than 0, then the neuron just gives an output of +1. Okay, this is another example of that F that I was talking to you about, the thresholding function. So it turns out, that in almost all hidden layers, we use functions like this, okay, the log sig function. Because see, pure line function means y is equal to wp plus b, because f is just linear. That is not very helpful. That is like linear regression, right? So you really want to be able to make use of the non-linearity and be able to capture non-linearity in the data. So in that case, f is very often chosen to be a log sig function, as shown over here, and it is very simple. It is 1 over 1 plus e to the power of minus n. Okay, that is a log sig function. Another function which is used very popularly is called as a softmax function. Okay, and the softmax function is essentially e to the power of minus wi into x divided by summation of e to the power of minus wi into x over all inputs I. Okay, that's a softmax function which is also very popular. So the softmax, so the log sig function is usually used for a 2-category classification, and a softmax is a generalization of that. Okay, let me go ahead. So now let's come to multiple inputs, single output still. Okay, so very simple. You have now P1 to PR as shown over here. So we just, each of those inputs has its own weight. So we just sum them up. We add the bias of that neuron. And so you can write it in a vector matrix form as shown over here. Okay, where Wij is, from algebra, it will be clear that it talks about the ith neuron connecting to the jth output as shown to you over here. More importantly, in the figure below, you can see that, drawing these will now become extremely difficult. And so we just have a P as an entire vector P. Okay, so everything will become just a vector. So it will be P or it will be X as my output. There is still a single input, and so this is an A, okay, which is a scalar. And this F again could be, for example, a log sig 1 over 1 plus e to the power of minus n. N over here, remember, is a scalar. So all the R inputs gives you W into P is a vector. Here it is going to be a scalar, so it will be W into P. So it is 1 cross R into R plus 1. So this is a 1 cross 1 output. This is 1 cross 1. So this is 1 cross 1. And then you just take the log sig of that. That will be the output. Now let's take it to multiple inputs and multiple neurons. This becomes a layer of neurons. So now I can talk to you about R inputs like before, but there are S neurons. So then when I write this W into P, okay, then this over here is S cross R into R cross 1. And then of course you have plus B, which is going to, because there are S neurons, there will be S biases. Each neuron, as you can see in the figure, will have its own bias. This is B1, this is B2, this is BS, okay? And this will be the output N. So you see that the basic does not change. The basic is still weights into inputs plus the bias. It could be a vector, it could be a scalar, or it could be a vector matrix. And in that way, you are able to get net. Now this net will apply to, is a vector. And so your activation function now will become multi-valued. So you will have F over here, you will have F over here, you will have F over here. So you're doing an element by element to this N. This N, remember, now is a vector. So the first element you apply F, to the second element you apply F, and so on. So people normally always choose the same F for the same layer. Okay. So, and as I said, you could use something like logistic sigmoid. So let's move forward. So we can now write this as an R inputs and S1 neurons in the first layer. So this is an RS1 neural network. Okay. I will still say this is a one layer neural network with S1 neurons in that one layer. So this is written in drawn in a vector matrix form. So you have W, which is multiplied by P. You add, so this is a summer. You add WP to B. You get your net. You apply a thresholding function and you get your output A or Y, which is S cross 1. Now this is a one layer of the neural network. What you can easily do is now repeat these layers to give you a multi-layer neural network, and that has been drawn for you over here. So you can see that the inputs are here. Okay, this is the input, which are our inputs. They go into the first output, first layer, sorry, and this over here is that first layer. What comes output of the first layer are these outputs A1, A2, and so on. The superscript here indicates that they are outputs of the first layer. They then go as inputs to my second layer. So I've just repeated this. So now note that this output has become an input to the second layer. Okay. And this input is then now weighted by a second layer of weights or a matrix of weights. And you get the net of the second layer, which then go through its own thresholding functions. Okay. And the second layer here is the output layer, because now the first layer has got sandwiched between the input layer and the output layer. So this I would call as an R, S1, S2 neural network. It has two layers. S1 is the hidden layer and S2 is the output layer. Okay, and it can be shown as a vector matrix form over here. R, S1, S2, A and N. Let me skip this for now, and I'll come back to that a little later. So let me now jump into how do you train a neural network. Okay, so we keep hearing training is a term which is used, and machine learning or artificial intelligence has borrowed or modified terms which are used as differently in other literatures. So for example, instead of training, I would call it estimation. How do you estimate, given Y or T and X, given the targets and the inputs, how do you find the weights and the biases? Because once I find the weights and the biases, there's nothing more remaining to be done. Given a new input, I can predict what is that output. That prediction could be either a regression or it could be a classification where it's a label like normal and abnormal. Okay, so let's see. So training is essentially estimation of the weights and the biases. So if I just go back, I hope you can see I've gone back to my multiple layers of neurons. You will see that my P is my input. I will take T as my target. So if I'm using target, this is known as supervised learning. Okay, and the reason that we call it supervised is because there are notions of unsupervised learning as well. But here, no, we will talk in terms of supervised learning. So I will use the terms P and T, or I might use the terms X and T. X for the inputs, T for the target. And Y is the output. So Y is the prediction. Okay, it is not given to us. Whereas T is your data. So for example, you are trying to do viscosity versus temperature prediction or some kind of a soft sensor as we call it. Of course, viscosity versus temperature, you will say there's no need. I know theoretically sound functions which connect the two, So, but just to take an idea, how do you do fitting? You will have temperature, you will have viscosity, and if you say you have mu is equal to mu naught into E, some Arrhenius kind of a law, you will then say, okay, my unknowns are E, mu naught, and this over here. Okay, so P and T will be your, so your temperature will be your input. So I'll call this as X, and this is your target T. Now, when you learn it, you try to predict Y, and this Y should hopefully, if you give the true training input, it should hopefully your Y should equal T. Hopefully, okay, if it did that work well. So, so you always start off with training data, and with the training data, you can arrange it in terms of because you can have many inputs. So each input, like P1 shown to you over here, is because there can be multiple inputs. So imagine you are trying to predict what is the purity of a compound in the distillate in a flow sheet, and you have multiple units over there. So your inputs cannot be just a scalar. There might be many things. There might be the inlet temperature of the feed going to the reactor. There might be the residence time in the reactor. There might be so many other temperatures, pressures that will play a role. All these will become an input for you. So your input will be a large, and how do you decide that? That is domain specific. So this will be P1 to PR. Okay, that is your input. Okay. And your target, you need not just make one prediction. What is the composition of the distillate is just one target, but you can have multiple targets. So you can ask yourself, what is the composition in the distillate? You can ask yourself, what is the tray temperature or the seventh tray temperature? Okay, this could be two outputs that are coming as a prediction out of your ANN. So even your target can be a vector. Okay. So what do? We take each input. So this is an input, one example. Okay, and this is one example in your training set where you have given an input and your target. So, but now you don't, learning requires a lot of data. And so you take your n different inputs and your targets, and you arrange them in this matrix T and P, with each vector being a row. So we put it as a row. I mean, that is just a detail you can skip. You can stop thinking about it now. So essentially, you can scale the data, just like in chemical engineering, we always scale our data. So similarly, you can scale the data. You can do mini-max scaling, or you can do zero mean, unity standard deviation scaling, and there are so many other options. Now, since there is data involved, this essentially connects directly with probability theory. So, you have taken a class on regression, and you would have seen some notion of such kind of an diagram where you have an input. So as shown over here, the input is thought to be deterministic. The output, however, is stochastic, or is a random variable. And you might have seen something like this: y is equal to ax plus n, okay, or plus w. Well, w will talk of the weight, so let me write it as n. So we think of x as a deterministic quantity, but we think that there is this noise, which is zero mean, which keeps on overlaying on my ax. And so instead of getting a single point, if there was no stochasticity at this x naught, I would have given you this y naught. But because there is stochasticity, as shown by this Gaussian kind of a distribution, the y corresponding to x naught could be anything. So if you know that if it is indeed Gaussian, and you know that plus minus 3 sigma take 99% of all the possible outputs, then y could be over here, anywhere over here. Okay, and so this is that the targets that you are observing in the real world are really stochastic variables. Okay, and we have to take we have to recognize that and be able to connect to that. Okay, and so let's see how ANNs connect. So essentially, ANNs take this viewpoint that T is stochastic. It has some, you will say some probability density for the targets, and X are deterministic. Okay, when you do that, you end up with frequentist methods where you're assuming that weights are fixed. So remember that I had n, or it was f of each neuron output was wx plus b. Okay, so we think of w as fixed parameters. They are not stochastic. Okay, we think of x to be a deterministic input. B again is an parameter, it is deterministic, so we get one y. Okay, but this y, on this y you add n, this gives you your target t. Okay, so your data that y gives you is not output y, but what you have is t, which is corrupted by the noise n. So this kind of a setting is the frequentist method, which is maximum likelihood is the approach that you take. The other approach, which in estimation theory is also known as regularization, and or MAP, which is maximum a posteriori estimate, you think of not only T to be having a distribution. You also say that my weights and biases have a distribution. Okay, that leads to a Bayesian approach, which is essentially trying to use Bayes rule. So you can see that this over here is the likelihood, and this is the distribution of the weights and the biases. Here I'm putting bias inside the weight, and so this is known as the prior. Okay, so you have a likelihood into the prior, which gives you the posterior, which is the famous Bayes rule. Okay, so one method is use a maximum a posteriori estimate, or the fully Bayes approach, the fully Bayesian approach then says that when I use this weight in order to make a prediction, okay, I will actually give you the density of the output as y is equal to the integral of your w of your output. Okay, so it will be probability of t given something, and I will marginalize it over all the weights w. So what I get then is not a point estimate, like so in maximum likelihood and maximum a posteriori I was getting a point estimate, but here I get a full distribution, as you can see by that orange band. Okay, and that is a fully Bayesian approach. So all these estimation theory notions carry on into machine learning. So let me look quickly as to what is a backpropagation, or what is this training method. So we have seen that you need data. We have seen that it is connected very strongly with estimation theory. Now let's look at what is this backpropagation algorithm. So I told you that if there were multiple layers, the notion of using multiple layers did not exist till mid-80s, and I think it was in 1986 when these kind of algorithms for finding out the weights and the biases, and remember now you have weight for layer 1, bias for layer 1, weight for layer 2, bias for layer 2, and so on, that these kind of algorithms started coming forward. Okay, so it was 1986. Rumelhart was one of the pioneers who proposed the backpropagation algorithm. So for those of you who have taken a course on optimization, you will realize that it is nothing but non-linear least squares in some sense, using some kind of a non-linear optimization like gradient descent or Newton's method in order to obtain those parameters W and B. Okay, but what he did do was very nicely arrange those calculations, that he would take an input and propagate it forward. So he would take an X, propagate it through all the layers and get a corresponding Y. Then he would look at the error, the difference between the target value and the Y, and then he would back propagate the sensitivities of these errors from the last layer to the first layer. Okay, and this was nothing but the backpropagation algorithm. It was backtracking of the sensitivities. So if I have to just show it, so you take a P, an input, you pass it through your layer 1, layer 2, till whatever, your final layer. This is your output, Y. You compare it with target, T minus Y, and you define this as an error. Now you backpropagate the sensitivities, that is essentially del E by del W. Okay, you backpropagate these sensitivities all the way back, and then you update your weights. That was the backpropagation algorithm. So it was, in some sense, a steepest descent kind of an algorithm, very nicely arranged through all those layers. Okay, so I've just tried to put that summary of the steps of backpropagation over here. So you can see that this is my input. I'm propagating it through all my layers. My capital M is the last layer. So it was R inputs going to S1, S2, and then this last layer had SM neurons. Okay. And then I calculate the sensitivities, and you can calculate it analytically, and you backpropagate them. Then, as shown in the last one, you update your weights and biases. So in addition to everything, it was a sequential approach of learning, which made it so, if you have looked at recursively squares, then instead of giving the whole batch of data in one shot, you give one data at a time. Give one input output training pair. Okay, so if I say that PI comma TI is one input output training pair, you do these 3 steps and you update your weights and biases. So you can see that they can iterate over here. So it takes the old value, this is your old, and it gives you a new value after having processed this input, okay, for the weights and biases. That was the backpropagation neural network. So now, essentially, this was great. I mean, people could solve that same exclusive OR problem, which was not solvable before, and it was working very well. However, and this issue is something which you all would have tried to see or you would have experienced. If, let us say, you have data which lies on a straight line, and you try to fit a 10th order polynomial to the straight line data, you must have seen that it gets very messy. So the data never really lies on a straight line, because any measured data has inherent noise in it. So although your eye can say, oh, you keep a pencil on top of your data and say, no, this lies roughly on a straight line. Okay, but machine doesn't have our kind of understanding where you can just look at it and say, well, this looks roughly linear. It actually tries to fit. So if you see the data that I have on this figure, the yellow squares, you can see that if you were to give too much freedom to the machine, it would try to do this, which I have called overfitting. Now you know that the figure on the left looks just right. So then if the machine asks you that, well, it looks right, but you've not got any point, you missed all of them, then you say, well, those points are noisy, there's noise in my data, I can't. That's why, whenever you do an experiment, you are always try to publish it, they'll say, what is your noise statistics? So how many replications did you do? Where are your standard bars? Because we all know that any real data is always noisy. So you would say that, no, the figure on the left is right. The figure on the left is a good fit, okay? Whereas the figure on the right is an overfitted case. That really, there is no such significant non-linearity in my process, or at least I'm not interested in it, if there indeed was. Okay. So this is the problem of overfitting. The problem of overfitting, and because you have so many parameters in your neural network, it is very easy to overfit your weights, and you can just count that if I give you an input which has 10 inputs, and let's say you put 20 neurons in your first layer, and you have one neuron in your last layer, you should be able to tell me how many parameters are there in the neural network. So you will say that, oh, this is 10 times 20. So these are 200 parameters right here, okay, plus the 20 biases. So it will be 220. And then you have 10 weights, well, you have 20 weights over here and, and one bias. So you have 241 parameters. So, you know, they can very quickly become highly parameterized kind of a problem. So there are two approaches that, so I should have really said that there are three approaches. One is early stopping that I'll talk to you about, one is regularization, and one is, you know, the fully based, what I talked to you about. So let's look at how we deal with early stopping. So what we do is we take the data and we split it into three parts. We split it into a training set, a validation set, and a test set. So again, if you had data, you would, let's say you had 200 data points, maybe you say, I'll take 150 for training, I'll take 25 or 30 for validation, and I'll take 10 points for testing. So I will take the examples in the training set only to train my neural network. I will not use examples from the validation or the test set to train my neural network. And but in order to, so what you have realized is that you give one data point at a time. Like I showed you in the over here. I've gone back to my summary slide, and I'm trying to show you that, see, we gave PI, TI, and then we predicted, we updated the weights and the bias. So it is one example at a time. So now if I take 150 examples in my training set, I will present those 150 one at a time and find the new values of the weights and the biases. Okay. I can, presenting all your data in the training set once is known as an epoch. So we call it, that is one epoch or epoch. Now, having presented this data for one epoch, you calculate the performance index, and I did not mention to you, performance index is very often the mean square error. Okay, the mean square error for most regularization problems, and we use a cross entropy for classification problems. So mean square error now comes very straightforward. If you assume that everything is Gaussian, then you can show that the maximum likelihood corresponds to mean square error. Yes.
Can it be possible that
yes, please go ahead.
Applies to reshare the presentation once, because we are getting very much delay from your side in that the voice is coming fine. So it sometimes this problem can be rectified if we will reshare the things. So stop maybe the presentation and the reconnect it.
So I should stop sharing and reshare it.
Yeah. Okay. So the sometimes it rectified this problem actually.
Idea.
Sometimes.
Let me do that.
Yeah.
So I will go to my.
You can
stop
the
presenting,
presentation and then you can reshare actually.
I can say present now. And, so if I were in Mumbai now, I probably
I know. That's so. There's the one question in the meantime. How do we give and select bias randomly, or do we select bias on some criteria? This is the question from Sarifuddin Jaman.
Okay. So can you see my slide now?
Yeah, we can see now. We are on slide number 21.
So yes. So you know, that's a very good point which I missed out. And essentially, so let me make it full screen.
Yes, sir.
Okay. So essentially, you see, we know how to start from, given a value WMK of the weight or the bias, how can you go to you can obtain the new value, No, this is what this equation tells me. But on the right hand side, no, I need to be able to calculate the right hand side. I need the old value of the weight and bias. So the question that Sharif is asking is very relevant. That what is the starting value? And you know the starting value of W, M, 0, and B, M, 0, the starting values are just some random numbers. Okay. We typically choose small random numbers. So you can use this as coming from some like a uniform random number generator, or you can use a thin Gaussian density. There should be values close to 0. If they are theoretically, there's no problem if you choose large values, but if you choose practically, if you choose large values, you realize that these are numerical computations and that there are gradient calculations and so on. You know, people say that it can run into trouble. So typically we choose small random values. Also, you will realize that this is a non-linear optimization problem. And so the notion of non-convexities is always there. That is, you're trying to find some minima, you're trying to minimize the mean square error, as I was just speaking about, or the cross entropy error function. And instead of getting the global minimum, you might end up getting a local minimum. And that depends on the initial value. So if you were unlucky, you might end up here. Your performance of the network will be poor. These are the weights and the biases. If you are lucky, then your performance might end up here. Okay, for the weights and the biases. So that is why linear methods have, although for all their pitfalls, linear methods are still there because they don't have any non-convexity issues. Okay, but yes, otherwise you have to choose these small random numbers. So who is your monitor? Who is keeping track of how you're doing? So you choose different values of the weights and the biases. Okay, yeah. So you choose different values of the weights and the biases, W0, B0, trial 1, trial 2, and always keep an eye on your validation function, which is what I was coming to the early stopping. Keep an eye on your training function, which is nothing but mean square error. So it is summation of E transpose E square. Okay, and if you get so if you try multiple times and you get once a value of E square, which is here, or J, which is here, the second time you get the performance index value J over here, you know that this gave you a better solution than the previous one. So J acts like a monitor for you. It tells you how well you were doing. Okay. All right. So we were coming to this early stopping, and what we said is that while you present your data to the training set, while you present your data to the training set, so this is your training data, you present it to your ANN. Okay, but when you want to check how good the ANN is performing, you actually test it on the validation set. So typically after one epoch is over, you then use this trained ANN, or after each epoch, and you apply it to the validation set. And from here, you calculate your performance index, that E transpose E. Okay, and you can then decide whether how good it was performing. So what you will see is that this is on this figure. I have drawn this J over here. Now, for the training set, this J, every time you perform anything, it is a gradient descent. It will only descend. It will go to a lower and lower value of the objective function for the training set. But for the validation set, it will go to a minimum, okay, and then it will start to increase, as shown over here. At this point, where the training, where the validation value of the sum of squared error increases, you should stop training. Okay, that is the point at which you stop training. And why is that? For that, let me go back to my previous figure. if my previous figure has come back, you will see this overfitting issues slide. Over here, at this point, your validation, so I will draw that same figure of J over here. Okay, this point corresponds to this performance, and once the validation goes up, this compares to, or this corresponds to this performance. So it should be clear that you should not keep on training. That means one epoch, then you give a second epoch, then you give a third epoch, and if you keep on doing this, we say that it is squeezing the information from the data into the weights and the biases. But unfortunately, beyond a certain point, the extra information that it is getting is essentially only fitting the noise. And if it is fitting the noise and it's a very complex, it has enough number of parameters, it will start giving you results like this, which you'll say is no good. So squeeze enough till you can get informative content out of the training data. Once its informative content has got squeezed out, don't keep on squeezing it, because then only noise will come out and it will spoil the performance of your ANN. So, so I told you that you should split it into 3 sets: the training, the validation, and the test set. So now training and validation is very clear. So what is the role of this test set? So the test set is a third set of data which is
Actually, I
completely
have a
independent
question here.
of. Yes,
Actually, in that you have shown
yes,
that
I can hear
described
you.
that a just right fit and overfitting, right? So in that case,
Yes,
overfitting means you are means considering all data points. Therefore, you are getting some zigzag type of fitting, and other one is the straight line type of fitting, just like a curve actually. So that looks nice. So in that case, we are always having some plus minus deviation from actual data point, right?
yes, yes,
Because the data points, some data are upside, some is downside. So we are at the center line of the data points.
yes,
And so it means we will always
yes,
have some means error from the predictions as compared to actual one. Is that so? Or I'm making a wrong
yes,
statement?
yes, yes. So yeah, you are absolutely right, and that is why if I were to plot, if I were to plot this and tell you that, so let me draw this for J for my training data set. If this point will correspond to this, okay, a much lower value for the training set will correspond to this, because as you rightly said, here there is less deviation between the blue curve and the points compared to the just right. In just right, there are larger deviations. So if you sum the square of the errors up, you will be over in the in that curve. You will be way up. You say, oh, my training performance is not good. But we as engineers know that if I measure, let us say, the temperature of my room, okay, I will see that I never get anything rock steady. I always will get some data like this. And if there are drifts, it might even give you this kind of drifts in the data. So I know that this extra data points which I am seeing, which are going up and down, is because of noise in the data. Okay, so I think of my output as y, which is a true output plus some noise. So I don't want to learn this noise. Why? The reason is because if I learn this noise, while it will do very well for the training data, it will generalize very poorly for a new data set, because noise does not repeat, it is random. So I do not want to learn noise, because if I learn noise, my value of the mean square error will be very good for the training set, but will start to deteriorate for a new data set for which I had not used, or which I had not used in the training. And that is the reason why we want to stop training early. We don't want to continue training. So if I have now moved to the next slide, so I am trying to show you over here
that over here is when you are still not, you're learning the major features of the data, not the noise. But beyond this, you are learning no new major features. You're only learning the unpredictability of that noise, which is present in your training data set. Remember that same noise will not be present in another data set. So the validation data set is acting as a check. Are you learning only the broad features or the information, or are you learning noise? Okay, and that is what you want to avoid overfitting by early stopping. I hope that is clear. Okay, so let me move on. Many times you don't have so much data that you will split into training, test and validation and so on. So there we do what we call as an S-fold cross-validation. In an S-fold cross-validation, we fragment the data. So let's say this is, we partition into 1, 2, 3, 4. Then we use the white part for training, okay? And this part we use for validation. We find out our statistics for validation. So we will find out JV, and we will do that same early stopping which we did last time with this data, with this partition. Now we do repartition it like this. So the second partition we use for the validation, then the third partition for the validation, then the fourth partition for the validation. If we do it this way, then we will have many different J's that you will calculate, because these were different data sets. And then you can average out these J's. And so this is an example of a four-fold cross-validation. Okay, and you can report that as your four-fold cross-validated performance of your ANN. An extreme case is when you, in your validation set, you only have one data point. So very often, you know, in clinical trials, you just have 10 people or some 12 patients. So here, in these cases, you can just use one data point as a validation data point. And the remaining 9 or 10 you can use in your training, but then you keep partitioning, and that is known as you know, n-1 fold validation. So in that case, it is also known as, very earlier days, it used to be known as leave one out cross-validation. So the advantage of using S-fold cross-validation is that you can use all the data for training of your neural network. Okay, that was method 1, early stopping. Now I'm going to come to method 2, which is known as regularization, and is one step closer to Bayesian approach. So previous one was completely frequentist. Now we're trying to take one step towards a Bayesian approach. Now, if you think about it, you know, essentially, you can say that my neural network actually calculates the posterior probability. So let's say I had class 1 and class 2. Okay, so let me take the example of class 1 being diseased, okay, and class 2 means healthy. Okay, now I do a blood test. My blood test is my input X, and I would like to make a prediction if it is diseased or it is healthy. Okay, so I'm actually trying to calculate this posterior probability. CK given X is what I'm trying to calculate. Okay, tell me what is the probability that if the input is X, then whether it belongs to a diseased state or a healthy state. Okay, so if you find out P of C1 given X, and for the same X you find out P of C2 given X, then the higher the posterior probability, you declare that you know it is diseased or it is healthy. Okay, now in Bayesian approaches, we use an idea of this posterior CK given X as the probability of X given CK. This is the class conditioned density, or what we know is the likelihood, multiplied by the prior. okay, divided by the evidence. So this is a very famous Bayes rule. The first term is the likelihood, the second term is the prior, the third term, the denominator is the evidence. So it is the likelihood multiplied by the prior divided by the evidence. Okay. You can show that if you were to assume that these all are Gaussian, okay, if this is Gaussian and this is Gaussian, you can show that this posterior is also Gaussian. Okay, and under that, the exponent of that Gaussian is essentially going to look something like this. So here I have assumed that, well, I need to back off. I probably uh, extended my analysis. I went into a slightly different part. So let me just back off a bit. Let me look at the time. Okay, it's 11:15. So essentially, I started talking to you about prediction. What I needed to talk to you about was the estimation part of it. Okay. So in the estimation part of it, I am not finding out the class. I'm not predicting. I want to find out the probability of the weights given my training data t comma x. Okay. And this again, I will use the Bayes rule. So I will say, oh, it is nothing but the likelihood t given w comma x. This is the target given the weights and the inputs multiplied by the prior. Okay. And you divide it by the evidence, which will be probability of x. Okay. So in this case, I want to, in case of maximum likelihood, we only use this part. And this gives us the mean square error if you assume that all these densities are Gaussian. But if, and you have assumed that W is deterministic, but if you now assume that W is stochastic, okay, then this also is Gaussian. Is normally distributed with mean 0 and some variance. In that case, you can show that the posterior is also Gaussian. Okay, and the exponent is essentially this term over here. So in addition, this term I already recognize as the mean square error, which is what I was doing in backpropagation, trying to minimize the mean square error. But what we see is that now a new term has popped up, and this new term corresponds to, this is what is a regularization term. Okay. People found that if you use only least square, mean square error, and you try to minimize it, then when the overfitting part starts, that means you keep presenting the data again and again, and it starts to do overfitting. At that time, we noticed that the values of these weights become very, very large. So you will find that some values of the weights are in million, minus, billion. Okay, they become very large. So people had noticed that even when it starts to fit noise, the values of the weights become very large. So if you take this Bayesian approach, it suggests that you should penalize the magnitude of the weights. This is known as regularization. So from probability point of view, it is MAP estimate, and just from a frequentist point of view, where you don't think of it as Bayesian, you say, no, I'm not going to minimize just the mean square error. I'm also going to penalize if the weights become too big. That is the frequentist way of looking at it. Okay, but it has a dual interpretation. So if you use this as your performance index and not like before, where you had only the mean square error, okay, then in that case, you need not do the splitting of the data and early stopping. You can use the entire data set, but just use this, penalize the magnitude, and you can go ahead with your fitting. So this alpha, which is more commonly in literature known as lambda, is known as a regularization parameter. The larger you make it, the more smooth will be your output of the neural network. Let me go back to this slide of just right and overfitting. So as you make your, so here again, you are not going to do any kind of splitting of data, but as lambda or alpha becomes larger as it increases, okay, you will get a smoother and smoother curve, which will correspond to just right. Okay, so that is the Bayesian approach. Now, people then said, you know, why use only the 2 norm of the weight vector? We can use the 1 norm or 0.5 norm or any other norm. And so for those of you who have heard of lasso methods, so this is known. So 2 norm is like this. So 2 norm, you all know, x square plus y square is equal to r square is 2 norm. The 1 norm is the sum of the absolute values of the vector. Okay, that is the 1 norm. That will all go over here. The sum of all these elements, if you see, is same, is 1. This vector is 1. The 1 norm of this is 1. The 1 norm of this is 1. This is a very popular regression method too. It's known as lasso. Whereas this over here is known as ridge regression. Okay, and then you can try other things as well. So this is the other way of doing of fitting, where you don't split your data, but you do some kind of a regularization. The question is, how do you know lambda, and what is the impact of lambda on your performance? And people can show that this lambda over here is nothing but, so if you think of it from a frequentist point of view, it's a weighting parameter. If you think from a Bayesian point of view, it's essentially nothing but the variance of W divided by the variance of the noise N. Okay, so remember now, W is also a is a stochastic variable, so it will have a variance, its own variance. So the variance of W divided by variance of N. Okay, so these are known as, so these are not direct parameters of the neural network, but they affect the direct parameters. So these are known as hyperparameters. Okay, and some of the recent advances seek to not only optimize the weights in the biases, they also seek to optimize the hyperparameters. Okay, so let me talk to you about some more recent neural nets. So I can tell you that backpropagation neural nets was tried very heavily by chemical engineers in late 90s. So for chemical engineers, who, like, for example, working in petroleum refining, they had tried all this out way back in the 1990s. And at that time, this overfitting issues and some other issues didn't make them, they were there, they were always there, but they had not overcome all challenges. Meanwhile, in the other areas, there had been a lot of other advances being made, particularly in computer vision. So our folks from the computer science departments were making a lot of advances in ANN, and this all led to this notion of deep neural nets. So in chemical engineers, we said never use anything beyond one hidden layer, because there is a result that mentions that one hidden layer with enough nodes in the hidden layer, or enough neurons in the hidden layer, can approximate any nonlinear function to any arbitrary degree of accuracy. So with that, we would rarely go beyond 1 or 2. But meanwhile, these CS people in other areas started going like 20 layers, 40 layers. So Google Net has 100 layers or 100 plus layers. Okay, and that was happening on their side. Now all of that has also become very mature, and I think one of the things that chemical engineers are now seeking to do is try to leverage those advances into our for our applications. So I'll just give you a brief introduction to two neural networks over here. One is known as the convolution neural network, and one is the recurrent neural network. After which, if time permits, I'll just give you some applications. So let me. Can somebody confirm that you all are with me? It's awfully quiet. So
Yeah, actually we can hear you. Only thing the slide synchronization is slight poor. That's fine. So
there's still a problem.
we can understand the
Okay.
connectivity the problem, but we can hear you means very clearly. So you can go ahead.
So do the slides shift at all, or they? So do
No,
the
they
shift
shift
slide at
actually,
all, or the shifts have
but
a
there is
delay?
some lag actually.
Uh, Lag. Okay. So my speech
Yeah.
and the thing don't synchronize.
That's okay because
Okay.
due to this connectivity problem, it may happen.
Yeah. Okay.
That's fine, sir.
So let me just give you a brief introduction to convolution. Yeah, convolution neural networks. So you've seen. I don't know how it is going in your colleges. For us over here, we have been looking at products, and we are seeing that there are already products for proctoring which are AI based, and a lot of them are essentially, if they're the candidate taking an exam, they have the video feed, and even if the candidate moves a little, it alerts Saudhan, the candidate is moving. Sometimes I think it goes a little overboard. But such products have already are there in the market. And one of the reasons for such kind of products is because they are doing this image processing. So, our friends from electrical engineering were always doing image processing. I mean, because it's a signal can always be processed. But there have been significant advances. So let me just talk to you how an image is stored. So an image, is stored internally, essentially as data. It has the pixel values and it tells you the intensity of each of those pixel values. So now, if what I've shown on the top over here, on the top figure, is a 4x4 image. Okay, but there are three color channels: RGB, red, green, and blue. So you can see that this is like a three-dimensional array. So, and the three-dimensional array is, one is the width, one is the height, and the third is the RGB, or the color channels as they call it. So if an image is essentially nothing but a vector, I can flatten this. I can make it into a 1D vector and give it as an input to my neural network. Okay. And I will be able to tell, for example, if it is a handwritten digit, I'll be able to tell this is 6. This is the digit 6. Okay. So one of these things is labeling. Given a picture, I want to be able to identify. So computer vision has that you give a camera takes a feed and is able to identify who this person is. If there's a person on the other end, it should be able to identify. If there is a car passing by, it should be able to tell this was a car going, or there's a truck going, or a bicycle going. Okay, so uh, uh, so images are essentially numbers, intensities of pixels. So if I can now take that as in my input data, and what is my target value? Target value is a label. It's a car, it's a man, okay, it's a cycle. Then I given an image, it should be able to tell me what is happening. It can give me a running commentary as to who is passing by on the road, for example. Okay. So, but the problem is this, that if you all have, we all take photographs with our mobile phones, and we all say, 13 megapixel, oh, 13 is outdated, 15 megapixel. So these images are very, very intense, or very, very highly pixelated. And so if you say that your image is for example 1084 by 1084 pixels, then those many elements in each color channel. Okay, so let's say it's 1000 by 1000, it means million elements per color channel. 3 color channels, 3 million elements. That is the size of your input vector. Okay, it becomes immensely large. So the people working in computer vision also realize that things are usually very correlated. If I'm wearing a red color t-shirt, the next pixel also very likely it will be red color only. So don't need to carry forward all that information with me. Okay, so they came up with these what we call as convolution layers. So there is a pre-processing layers to a neural network. So there is a neural network which is a backpropagation neural network, but before going to the neural network, there are these convolution layers. And as I have shown written down, that there are these pooling layers. So there are two different type of layers. One is a convolution layer and one is a pooling layer. The convolution layer typically relies on a ReLU kind of activation function. And if you're wondering what is ReLU, it is nothing but, so I will write here, ReLU of x is equal to maximum of 0, x. So if x is positive, it will give you that same number. If it is negative, it just gives out 0. Okay, it's a very simple unit. And why is that? Because intensities are all positive numbers. So it should not happen that I do some manipulation and then I give you a negative intensity. Okay, so ReLUs are very popular for image processing. So I will try to briefly talk to you about this convolution layer. So you will have a convolution weight, and let me write down this weight: 1, 0, 1, 0, 1, 0, 1, 0, 1. Okay. What it does is it takes a patch. So if you can see over here, this yellow part is a patch. It takes a patch by patch of that image, and each intensity it does a dot product. Okay, element by element product with this convolution weight, which I have written down W over here. So for example, if you can see, they have given, so 1 multiplied by 1 is 1, then 1 into 0 is 0, and then it adds everything up. And you will see that the answer is 4. So the convolved feature has a value of 4. That is a convolution layer. Now, if you're wondering, no, what is this 1, 0, 1, 0, 1, 0? So it was well known that, see, whenever you do touching of an image, you retouch an image, you can make it sharp. Most of these apps will allow us to make it sharp. They will allow us to make it blur and so on. There are these well-known filters. So there's a filter to make things sharp. There's a filter to make things blur. There's a filter to change the brightness. Okay, and this is essentially the same operation. So you're filtering that image, and this is known as a convolution filter. After that, so that is one layer known as a convolution filter. The second layer is known as pooling. See, because this information is too big, this information is too much. So before I go to pooling, let me tell you that then it will, after it finishes the first one, it will apply the convolution weights to this. Then it will move one more further down or further to the right. So it's called straddling or striding that image. So it takes patch by patch. The patches are most of the times overlapping, and it just goes one by one, and then it will come down one row, and it will do that entire operation. Okay. In the pooling layer, it takes it essentially does a dimensionality reduction. So this is the convolved unit. It takes, let us say, 2 by 2. Okay. It finds out the maximum value over here, and so this is known as max pooling. You can take average, you can take max. There are many other options, and this 6 you write over here. So here we don't do overlapping. Okay. So then we go to the next patch of the convolved unit, and we see that the maximum value is 8. We write 8 over here. okay, and so on. So this does a dimensionality reduction. So they were saying that if it is 1054 by 1050 or 1000 by 1000 image, it can do a dimensionality reduction and bring it into a more manageable size. Now you can have many convolution filters, you can have many sub-pooling or sub-sampling filters. And after these initial filters, it goes to a backpropagation neural network. So the backpropagation neural network, which we discussed, is still applied, but you have these extra filters. The other point is, the filter that I wrote on the top over here, the value of W, is, these are well-known filters for sharpening, for contrasting, but you don't want to be stuck with them, because you want to use that filter which is right for me to get my solution. And so it does not take these standard filters, but these are all parameters. So this will be some W1, W2, W3, and it will also identify these parameter values. Okay. This is how it becomes a deep neural network. So I've taken this slide. So I realized at MIT, I think OpenCourseWare, if you type deep neural nets, there's some very nice set of 1-hour tutorials which give you, so if you go through those 3-4 tutorials, there are some grad students who have done an excellent job, and you get a sense of that subject. Okay, so here they are showing a car image which goes through this convolution with ReLU. Then you have pooling, you might have more convolution, more pooling. Okay, and then finally it all goes into this deep neural network. So these will be from the pooling layer, they will all get connected. These will become inputs which will get connected to your neuron. So this is your first hidden layer, second hidden layer, third hidden layer, fourth hidden layer, fifth hidden layer, and then this is your output. So you can see that this is a deep neural net. Okay, so it has huge number of applications. For example, if you have a dirty environment, let's say in some mineral processing, there's too much, you've taken an image, but you can't figure out where is the level, okay, level of, let us say, the processing level and some level on top of it, okay, and you want to be able to find out the interface. So you can use a deep a convolution neural network. You want to find levels. So I remember Professor Manibhushan in my department, he set up a webcam, his laptop webcam, and some level, and he could monitor the level just by using his webcam image going into some processing tool, and which would tell that it is at this height. Okay, so there are many things which I think we can also do in chemical engineering in the industry. Okay, on the right side I have written some standards. So see, these neural nets are like already pre-trained, partially trained. So you can use one of these partially trained neural nets and just tailor it to your application. Okay, so you must be hearing about this driverless vehicles being so popular, and they all are based on convolution neural networks. So they do what is known as an image segmentation. Given an image, they will tell what are the different parts of that image and so on. Okay, let me do my next neural net, which is a recurrent neural net. Because in chemical engineering, we often deal with dynamic data. It's not always thermodynamic or steady state models. Very often we have dynamic models. So the point is like time series data. So we know if you write a transport model which is not steady state, like thermal transients, okay, you know that the output depends on the previous values of the output. The temperature depends on the previous values of the temperature. So this is correlated in time kind of data. So for this, there is a notion of a recurrent neural net. And if you're wondering what is a recurrent neural net, so it is something like you have an input X. So this could be the heat supplied by a heater. Let's say there is a resistive heater. Okay. And this is an element whose temperature you're measuring. So let's say this is the temperature. And T is the time. So it tells you how this is varying with different inputs that you are presenting. But how is the time series evolving? Okay, that is example of a dynamic data. So we know in chemical engineers that whenever you write a model which is d by dt or something, time has come, means you will plot something versus time, you will get a time series data. Okay. So, way back in 1989, when backpropagation came out, people said, well, we can easily apply it to time series data. And the reason was that you can open up. So if this is my feedback, which is telling me temperature at T, see, temperature at time T is a function of the temperature at time T minus 1, comma, x T minus 1, and so on. Okay. So I will say, okay, I will open this. So this temperature at T minus 1, I will take it as an input to temperature at T. So if you break this, or you don't break it, you open it up, then you can see that this is like a feed forward, a deep neural network. This is your temperature, let us say at time t is equal to 0. This is your temperature at time t is equal to 1. So now you have got that time series data. And these are your heater inputs. How were they changing with time? So if that is the case, you can apply backpropagation neural network straight in a very straightforwardly manner. But it turned out no, that it was not the case. When people tried to use, so theoretically you could, but when practically people tried to use, so this backpropagation through time, this algorithm came to be called as BPTT, and it was by William and Zisper in 1989. It was not found to be successful, and the reason in a subsequent paper by Hawkwriter and this Schmid-Huber, they figured out that the problem is that in these neural networks, there is a problem of vanishing gradient. So remember, these all are gradient descent kind of algorithms. So you know that, steepest descent is the new value of the weight is equal to the old value minus the descent direction. I'll just write it as or gradient direction, negative of the gradient. Okay. So this negative of the gradient, either people saw that it would explode or it would vanish. And one of the reasons, let me go back to the previous slide. Now there might be some delay, but the difference in a recurrent neural net and a feed forward and a feed forward neural net and a recurrent neural net which is acting as if, and a feed forward neural net which is acting as a recurrent neural net is the following: that in a feed forward neural net, all the weights and biases from layer to layer had to be different. Okay, we called it as weights with superscript 1, weights with superscript 2, and so on. But just think about it, in a recurrent neural net, even if you open it up, these weights cannot be different. You cannot say that if let us say you are using a thermocouple and you want to find temperature, and you find this something like the temperature is equal to alpha times the millivolts plus some beta. It cannot happen that this alpha and beta keep on changing with time. So in a recurrent neural net, when you open it up, it is just different. It is the same weights. The weights and biases should be same because it's the same layer. It's just the time that is changing. You cannot have there's some alpha 1 at time in your first time step, alpha 2 at second time step. So all these weights, W1, W2, cannot be different. They have to be same. So when you force these different weights to be same, we find that there are these problems of either vanishing gradient or exploding gradient. And this comes about, because when the weights are the same, you keep multiplying. So if you keep multiplying 0.8 multiplied by 0.8 many times, it vanishes. If it is some 1.9 into 1.9, because these values have to be same, it starts to explode. Okay. So then, people's the same Hawkwriter and Schmid-Huber, said, came with some proposal. And this proposal came to be known as an LSTM network. It's a long short-term memory network. So they proposed some different some ideas. Okay, and very briefly, it says that, see, when you go from your one open your neural network like before, but in each neuron, this is known as an LSTM neuron. Okay, we will use gates. So this is the cell state, the previous value of the cell state. So for, if for in controls we talk the state space models, so we have a state and we have an output. So here the H is like that output and C is like that cell state. It is the memory that is being carried forward from one time point to the next, to the next, to the next, and so on. So they had an what they called is the forget gate. So this is the forget gate. Okay. So in the forget gate, uh, depending on this input, it was decided how much of the previous memory should be taken forward. That was step one in calculation of an LSTM network. Step two was that how much of this input X should be taken forward. Okay, and these sigmas are nothing but log sig. So you remember that this log sig always went from 0 to 1. 1 over 1 plus e to the power of minus n. So if the output was 1, then we said that the gate is fully open. If the output is 0 or close to 0, we said the gate is closed. So it was just modulating everything. And then you had an update of the cell state. So this was the input gate, and this is known as a 10 hyperbolic gate. Okay. This over here was used to update the cell state. So they would make a candidate state, C tilde T. So C is the cell state, which is the memory of the cell. Based on the input, they would make, and this 10 hyperbolic layer, they would make a candidate cell state. And then the candidate cell state and the input gate would decide what is the new cell state. So this is CT. And then for the output, the new output H of T, there was another output gate, which is again a 10 logs logistic sigmoid. And that is how one single neuron, an LSTM neuron, was based on. Okay, with simple calculations. So they essentially made it more complex because they figured out ways of making sure that this gradient does not vanish or it does not explode. And this became very popular again. They, so for example, Google Voice, which we all use in our mobile phones, is a recurrent neural net, LSTM neural net. And you must have heard of stories being written by artificial neural nets. There was a time when, you must have seen research papers written by artificial neural nets, music composition done by artificial neural nets. So you must have seen a lot of these messages I get where the lip is moving, but it is not that person talking. So you can really subterfuge or spoof somebody's voice. There are faces. So in that MIT, one of those things, they showed us 3 faces and said, all these 3 faces are made by, they're not real persons. They have just learned and they have made it using an ANN. So there are all these exciting applications which are there. I have about, so I'll conclude in around few minutes, 2-3 minutes. So I'll just talk to you about a software, which again is completely free, and if you can start using it right away. It's known as TensorFlow, again originally built by Google, and there is this Keras, which is a high-level API, which is very easy to use. And Keras is actually built on top of TensorFlow. And using Keras, you can just start working right away. Uh, I will not go into applications now. I will share these slides with Professor Arya, and he can share them with you. I'll be more than happy if you have any questions. But there are many applications where ANNs can be used in many control toolboxes. Way back in 1990s, people were using ANNs as a nonlinear compensator. There was one company called Pavilion Technologies that had started using ANN models. So it's been around. The difference is really this, that as the technology becomes more and more complex, the ability to use it also requires higher level of training. So for example, I can ride a cycle, I can probably drive a car, but if you tell me now you have to fly a plane, then it becomes more complex. If I tell you now you have to fly a rocket, it'll become even more complex. So the person who is doing it, has to be more and more trained. So I think in some sense that the challenge for us as chemical engineers to be able to bring these things into the industry has a lot to do with training, ability to use it. Many a times, any advanced methods which are used in the industry stop getting used after the consultant goes away, because the operators say, well, firstly, we cannot understand why it is trying to do a particular action. The level of explainability goes down. And and secondly, you have to upgrade yourself to be able to use it. So, there are some applications which I had over here, and I will skip these. Maybe you can go through them. What I could do is just show you in R um, how to do some coding. So I've just downloaded, and the amazing thing is that there is so much information on the net that none of these codes are written by me. Most of the diagrams, and I didn't have time to give enough acknowledgements. A lot of those figures I just ripped off the net. Okay. So what I'll do now is probably I'll just talk to you a little bit about how to code for using Keras TensorFlow. And I was saying you can do it in Python. I use a bit of R, but it's extremely straightforward. So in R or in Python, there are libraries. So you will have to download these libraries. There are a lot of data sets which are there on the net. So I've taken this CFAR, which is a Canadian data set, which has 60,000 images. And there are 10 different types of images. I mean, 10 different classes. So for example, there's an airplane, automobile, a bird, cat, and so on. Now, the point is, with these 60,000 images, you are supposed to identify, and I had already plotted some of these over here for you to see. So I'm not sure if you can see can you see my R Studio images which I'm displaying?
No, actually, it will come shortly. Yeah, we can see now.
Okay.
Yeah.
So these are those 60,000 images. Either it's a bird or a deer, an aeroplane. So there are 10 classes. Okay. And so I'm going back to my R code. So building the neural network is extremely simple. So I'm going to highlight this and just talk to you so I can connect it to what I was discussing as to how to model it. So see, this layer, and layers have this name. So it says layer convolution 2D. So it is using a 2D convolution layer. In that, it is using 32 filters, not just one or two as I was talking, where it was doing that convolution or image feature identification. You can see that the activation I'm using is value, which is nothing but max, is the positive value of that or max of 0, x. this is the image. So the image for me now is a 32 cross 32 pixel image. And it is a colored image, so it has 3 channels. So you can see that the input shape says it's a 3D array, 32 rows, 32 columns, and 3 width in terms of depth. Then I'm using this pooling. So remember we were doing this max pooling. It is going to do the same pooling with 2 cross 2. So every patch will be 2 cross 2. In convolution layer also you can see that the kernel size is 3 cross 3. So the patch will be 3 cross 3. It will take every 3 cross 3 pixels and keep sliding. Then it has the third layer is again a convolution layer. The fourth layer again is a pooling layer. The fifth layer is again a convolution layer. Okay, and there's a nice command in R called summary. So if you hit on summary, it'll just show you the neural network in form of. So you can see that the neural network looks like this. So it shows you how many layers are there. Now the last convolution layer, because I added that later, but I have not done it right now. Before the class itself, I had just looked at it. I have flattened all those inputs after my last convolution layer. So you can see that there are 1024 inputs. So it's a reasonably large sized input, but in image processing they'll still call it small. And then is what is written as dense is a backpropagation neural network. The 2 layers. So this is the flatten is the input layer to the backpropagation, and then you have this output layer, which is dense 1. You can see that the total number of parameters in this ANN is 122,570. So now you know that these deep neural networks, they really work with large kind of how can I go back? Where is my editor? I put up. Now I'm not able to. Okay, there you go. I've come back. Okay. Then you compile. So you tell your training that I want to use cross entropy. So I didn't really get a chance to talk about cross entropy. If you assume that your classes belong to a binomial distribution or they are Bernoulli outputs, then you can show that maximum likelihood gives you, instead of this mean square error, it becomes slightly different. It is known as cross entropy. And then there is just so you tell that try to use that as your metric, as your loss function. And then there is one very simple command to start modeling, to start fitting. It's just called fit. See, now you'll see that I've given the epochs 8. I have also split it in such a way that out of the 60,000 images, 50,000 are going in the training data set, 10,000 are going in the validation data set. So that we can try to see the data set. Now I gave the training, but it takes around 10 minutes to train it. And so what I had seen here was the output of my training when it was giving me this epoch. So you can see that at 1 out of 8, 2 out of 8, 3 out of 8, and it keeps looking at this accuracy. Accuracy is 2 positives plus 2 negatives divided by total number of data points. So in classification, we have true positives, false positives, so which were correctly predicted, and that is called as accuracy. So you can see that it was 37%. It started to rise. Eventually, it went to around 71% after 8. Okay. Now you should be able to see at your training data. And let me just zoom this again. It'll probably take some time before it plays out. If you can see this, the top one is the loss function. Red dots are the training data. The green dots are the validation data. you can see that the training data keeps going down significantly. The validation data stops going down significantly. In fact, at epoch number 5, the validation loss function was slightly higher than that at epoch number 4. And then it more or less settles down. So beyond this, it is learning noise. Okay, so that is early validation or early stopping. So using the word stopping triggered in my mind that it's 12 o'clock and I also have to stop. So let me stop right here. So let me stop my presentation. And I know I have again as always overshot my time, but I'll be happy to take any questions if there is time, depending on how Rajkumar. Yeah, Rajkumar, over to you.
Actually, thank you very much, sir. And actually, I tried to learn because I was thinking to learn the machine learning from a very long time because I want to fit my data or diffusion in polymeric coatings. Uh, so I learned, so due to some technical these glitches, we cannot synchronize slides with voice, but still we have all these things. And it is really a very so one thing I the surprise, the one thing that writing the research paper by these machine learning techniques. So if this thing really would happen true, it would be a disaster, right? What do you think?
Yeah, what it can do is it can compose music
Okay.
because it gets trained. So you feed it many musical compositions. Let's say if it is Carnatic music, so you feed it many Carnatic or Hindustani music, then it learns how to correlate. After this note, mostly this note comes. So then you can give it a starting value and it will make one musical composition. Same way with research papers. If you or a story, it can try to write a story. And yeah, so again, technology is agnostic. It really depends on how we use it. So
Yes.
that thing comes again and again.
So second thing is that I means if for a beginner actually for time being for myself, if I wants to learn and start it, is there any some particular book which you want to suggest that it would be good for a beginner to start with?
So what has happened is in so I can tell you what I did.
Because I can tell one
So
thing
I
for
also
MATLAB
decided that
actually when I just
uh,
learned the MATLAB, I took a course in IIT
yeah,
Delhi during my master. I didn't understand anything actually. So when I went to PhD at IIT Bombay, I learned everything by doing program. I have not seen even a single book actually. So MATLAB command window
yes,
and with the help of your student, then
yeah.
in the Nitin Padyar and with the help of my guide professor Madhu
uh,
Minjabu, I learned everything by that way. I have not seen even a single book. So if there is some other
this is
some
this is very
software,
true.
some
So this is very true about these convolution neural nets, recurrent neural nets. What completely amazed me that these there is so much information on the net that if you first have that basics there, then the books will not be able to give you beyond a certain point because it is changing very fast. By the time somebody learns and tries to write a book, it changes very quickly. And so what I will say is one can take one basic course on neural net. The book which I had followed in the early days was by neural network design by Hagen. And I was very fortunate that Professor Hagen taught me neural nets when I was doing my PhD. And but that book is now outdated. So there is a book which one of my students, or he was my student. He's now at IIT Delhi, Hari Prasad. So I asked Hari, because Hari is more recent. So I asked Hari which books. So Hari suggested to me a book by by Bishop. So Christopher Bishop, Pattern Recognition, is one of the books that he suggested. Um, that book is very mathematical. So if you had a good probability foundation, then it is easy to use. But it is a free book. So if you just go to Google, type Pattern Recognition Bishop, it's a free book. He's made it available for free. The other book which Hari told me is more useful is by Hasty and some others, which is more applied, little bit more applied. But I can tell you that finally I had to, so I used Bishop. First 5 chapters, 5th chapter is neural networks. So the first 2 chapters are just introduction and probability. 3rd chapter is linear regression. 4th chapter is linear classification. 5th chapter is neural nets. So till that much, it gives you enough basic, after which you will have to go on the internet and try to figure out how to do this coding. So all my codes I have taken are from the net. I have not written any code of my own. But it is very straightforward. And once you like LaTeX, like somebody gives me a LaTeX file, and although I may not be an expert in LaTeX, I'll start using it because we do pattern recognition ourselves. So through that, one can get started and move towards applications. And then after some having made your hands wet a little bit, it is easier then to follow theory. So I agree with you, Rajkumar, that the best way is just start up, take one simple problem, maybe even fitting a sinusoid, like given in Bishop's book. He tried to fit a sinusoid. And then once you start coding, you can start using with some information your own ideas, and you get started.
Okay.
That is what I would
And
suggest.
yeah. Thank you very much, sir. And one any question from participant side, they can quickly ask before the Professor Sharad leaves.
Siddharth.
Yeah. Sir, the number of neurons, how the number of neuron can be optimized?
So Siddharth's question is essentially like, now you have so many layers. How do you decide how many neurons are needed?
Yes.
So, one straightforward method of doing it is you take different options. Now, so you have 10 neurons, make it 20, make it 30. I'm talking about, let us say, just one hidden layer.
Okay.
Now you do your training using the training data set and the validation data set, but
Okay.
look at the statistic on the test data set, which has never been used either in training or validation.
Okay.
Now compare how was the performance on the test data set.
Okay.
You will find that beyond, when it starts to become too complex, then you will find that the test performance will start to deteriorate.
Okay.
This is the frequentist approach of doing finding out how many neurons are there.
Okay.
This corresponds to what in estimation theory we call as Occam's razor, that you should choose the simplest possible construct that can explain the data.
Okay.
But Bayesian approaches take a slightly different viewpoint. Bayesian approaches take a viewpoint that we will there's a notion of effective number of parameters. So even if you use a Bayesian training method, you will see that your code will report to you the effective number of parameters, and the effective number of parameters corresponds to that. Though there were 200,000 parameters in my neural network, effectively I have used only 1,000.
Okay.
So here the approach taken is, you can take it as complex as you think. We will use as many parameters effectively as needed. So this is a slightly different viewpoint, that although it is a very complex looking neural network, during the training phase, we have used effectively much lower number of parameters. So you must have, so in neural nets, many a times, there is something called a drop. and a drop is a layer, or is the property of a layer, which says that at every epoch make 40% of my neurons, make them zero.
Okay.
This comes from the point, that see, even in a, when these people do neural experiments, even if a person is slightly brain damaged from one side, they find that the brain has these parallel connections. There are many, many connections trying to solve a problem. So even if the brain is damaged on one side, through other neurons, through other pathways, you can actually try to solve that same problem. So to mimic that, people have done, this is true in TensorFlow, that it will ask you to, or that is one of the layers where you can say that you drop 40% of the neurons. So in that case, you end up with far lesser number of neurons than you have put. Only a far number is lesser number is used. So there the answer is really, you use what you think is right,
Yes,
but
yes,
the
yes.
training will take care of it.
And sir,
Then the patient
one more thing, sir. When I have a data set, so in a hidden layer, should I use a TNSeq, logseq, any thumb rule for selection of the this function?
So
When to go for TNSeq,
in
when to
the
go for
old
logseq?
days, yeah. So in some sense, no, it is like this, that if I give you a some data, you can fit it using, let us say, a polynomial basis, or you could use a Fourier basis, like trigonometric Fourier basis, or some other basis. So from a very fundamental viewpoint, you think of these activation functions as some basis functions. So it should not matter. You may require a different amount of neurons with different bases. Maybe one is more efficient than the other. So if it is a sinusoid, I'm using sinusoid basis, it will be much, I can do that fitting with far fewer number of sinusoids. But if it is a logarithmic, or I'm sorry, a polynomial function, and I'm trying to use sinusoid, I'll need much more number of basis nodes. So typically all of these have the ability to work as a basis function, and one may be more efficient than the other. So again, logistic sigmoid is very popularly used. Tan hyperbolic is very popularly used, and maybe in one problem one may be better than the other, but it has not really been a point of contention, is what I'll say. So in that sense, it has been fine. Yeah, you can try, and you may find that for one problem, if you do that exploration, that one might work better than the other. But I think there is no clear answer.
Okay.
Yes,
Hello. Hello.
Dr.
Hello.
Jalesh.
Yes, Jalesh.
Hello,
Good to
sir.
see you.
This is Jalesh. Yeah.
Yes,
Good
Jalesh.
to see you too, sir.
Yes.
Sir, these days I came across a couple of papers on machine learning based Kalman filter. So how it is different from conventional Kalman filter?
So, I myself have not looked at any paper. I would have loved to see some paper, but I can imagine that there are probably many ways in which you can use a machine learning for in an estimation or in a filtering theory framework. The most straightforward that I can think of is that let us say you have a plant, you don't have a model of it. So you take the input output data and you generate a machine learning model. So instead of generating ARX or RMAX, you can generate a machine learned model and then use that in a standard EKF framework, extended Kalman filter framework.
Yes.
So that could be one way of doing it. The
Very
other
few
way
papers. Very
is,
few
as I
papers are
told you,
there.
that and the other way which I can imagine is that, see, even the machine is giving you posterior probability, which is exactly what Kalman filtering is doing. Kalman filtering is saying what is the state given the output.
Yes.
And that is exactly the same problem that it is also solving. So so in estimation or in statistical learning theory, there are really two parts. One is statistical inferencing, and one is statistical decision making. So if you use the machine as a decision maker, it is also doing like a Bayes rule. So it is finding the posterior. So maybe in that framework, one could use a machine for in place of a Kalman filter, or to mimic a
Yes.
Kalman filter.
Okay.
Uh, One more question from Mr. Neeraj Agrawal. Can I use deep learning model with just 30 training data for regression model?
Yeah. So so many like years earlier, before this Bayesian started becoming popular, it was always very problematic to have very few data points, and you are using some kind of a fitting. Let's say you have 30 data points and you are using 2000 parameters, and it used to always be very problematic to be able to do that. So now, I have myself not done with few data points, but what I see is that if you're using a Bayesian approach, where you are using regularization, then it is indeed possible to be able to use a neural network. I will not say deep neural network, in order to be able to do some learning with fewer data points, with, let us say, an S4 cross validation. So you have a leave one out kind of a strategy, and so you will estimate 29 neural networks, and the one you will validate on that one data point, and you can try it. I am more of an a cynic in this regard. I'm a little bit cynical about this, that whether it is indeed possible to use, let us say, with 5 layers and many things. Uh, I myself don't have an experience in it. I know that with a frequentist approach, it will not work. But with a Bayesian approach, um, it may work, because as I told you that if, let us say, so for example, if you're using MATLAB, the command is train BR, train Bayesian regularization, and at the end of the training, it will tell you how many are the effective number of parameters. So as long as the effective number of parameters are not higher than, let us say, 1/4 or 1/5 of your total training data set, it should be okay. So it is like that brain that, although it's a very complex brain, but it's using only few pathways. So it is using many pathways, but it is not using all the neurons. So as long as you keep an eye on effective number of parameters, it may be possible.
Thank you, sir. And one last question I think we have, that the one from Syed Sam Ali. He has some experimental data. I don't have any model in the literature that related to this study, but I wish to do modeling using ANN. Then how do I do?
What was the first thing you said, Rajkumar? What
What
data you have?
he
Or
has some
Syed has?
experimental data, but doesn't have model for that. So
Experiment.
if he can explain
So
some physics about that, I think then you can give some idea, right?
no. So the holy grail, no, or the big promise really is that these are black boxes, and whether, like Syed says, that he has experimental data, no idea of
Yes,
what is the underlying physics, just
correct.
input output. Now, the first thing is whether the inputs that you have in your data set fully determine your output or not. I'll give you a simple example. Let's say y is equal to u plus v. And if you are trying to fit a model between u and y as your input and output, and you have left out v, and if v is constant, you will get this model. But if v keeps on moving around, you can never explain y completely. And in that case, you will not be able to do a good job. So yes, if you have experimental data and you understand, even if not from a physics, at least you have a feel that, if these things change, then my output changes, and they become part of my input. I can definitely build a neural network kind of a model. So the answer is yes and no. It really depends on our understanding whether all that inputs, which the input vector has sufficient information in it to be able to explain that output. If it can, then yes.
So I would say that, sir, thank you very much actually for accepting our invitations and to managing time in such a tough situation actually, to managing technology, presentation, arrangement, so many things, and giving such a
Yeah,
informative.
I think no, Rajkumar.
Yeah,
Yeah, I think, see, because of this lockdown and there being no presentations or no movement of people, otherwise, at least faculty, we would meet each other in some workshop, something. So it's very
yeah,
good that, you all have taken this lead to make, at least we can meet and, exchange our ideas. So
yeah, yeah. This is
I also express my gratitude.
yeah, and with this, I will say thank you very much once again, and thank you for all the participants for joining and patiently the listening the talk actually and giving a wonderful interaction. So we will close this session here. Our next session would be at 3 o'clock, and topic of that talk is numerical differentiation and integration by Professor KNS Kasi Viswanan from NIT Warangal Department of Mathematics. So we will have that session at 3 o'clock. So with this, we will close this session, and thank you very much once again, sir.
Thank you, everyone.
Yeah, yeah, thank you very much.
that I watched last month. Actually, I
Hello, sir. Good afternoon, Dr. Kasi. Hello, sir. Good afternoon. How are you?
Fine, sir. Just now I joined, sir. I think I was in
Yeah,
time.
yeah, yeah, you are before time actually.
Yeah.
We have still 8 minutes to go actually.
Okay. Thank you.
So, how is climate at Miss NIT Warangal?
Climate is
Is
okay, sir. Now
hot
it is
or
a
it's
yeah,
yeah?
winter season. Night time, the temperature is going up to 14, 15.
Okay, 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 okay.
But in the campus, it will be 2 degrees less because of greenery.
Yeah, yeah. I visited actually the campus 2, 3 times.
Okay.
It's very green, actually, full of trees. And this Professor P.B. Rao has planted so many trees there.
Yeah. Now it is full, sir. Every student who is joining, they have to plant one tree.
Yeah, yeah. That's good. Actually, that's good initiative actually.
Yeah.
And moreover, we should start that initiative around the nearby area also. That would also be the benefited actually.
Yeah. So based on that, every year for the past 4 years, 10,000 trees were planted.
Okay, that's good, good, good.
Every year,
Look at the
approximately 2,500 trees.
yes, yes, good, good. So Professor P.B. Rao and me, we were colleague in BITS Plani Goa campus actually.
Yeah. He came from there
So
only.
yeah, yeah. So he went to your side. I went to this JP University, then Thapar University, then now NIT Warangal. I mean Jalandhar, sorry.
Jalandhar.
Yeah, yeah, yeah.
Uh,
So how are the classes, exams of the this semester? Means
yeah,
the
it's
is
a
it over?
completely online, sir. Completely online.
Oh,
And the classes we are everything we are taking. Classes will be Google Meet or WebEx and something like that we are conducting, or even from
okay, okay.
Microsoft Meets. And whereas
Mm-hmm.
exams is considered LMS only, through LMS only we are conducting.
LMS. How does it work, Matlab?
Yeah,
Means
LMS, it is
LMS.
working well, sir. It is working well. But means we are giving multiple questions and everything. For example, about 50 students were there. We are suppose
Okay.
if we are asking them to answer 6 questions. So see, same cognitive level, we are setting 3 questions, and we are
Okay, okay,
making
okay.
shuffle within the question shuffle, and then at the global level also it is shuffle.
Oh, oh. So
That means
it's too much
some
work as a teacher actually. It's too much work at that
instead of
time.
6 questions, I am setting 18 questions now.
Yeah, yeah. 18 question again corrections of those also. Soft copies
Correction.
correction is also painful.
Yeah, correction on the screen only we are doing, and
Okay, okay, okay.
they can upload by either PNG file or a JPEG file, or otherwise
Okay.
PDF file.
Okay, okay,
So
okay,
if we
okay,
use
okay.
the Mozilla Firefox browser, so then automatically
Uh,
on the screen everything is coming. We need not to download and keep in separate folder.
okay, 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 okay.
And then we can make a comment. Also, there is one comment column will be there, and marks also we can avoid there itself. We can write a comments and everything. But the only thing is we cannot make the corrections. That means tick marks and all those things. Those things we may not do.
Yeah, yeah, yeah.
Some
So what do you do for the tick mark thing?
the tick mark we are not doing anything. But the only thing is we are making some comments and we are avoiding the marks.
Okay, 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 okay.
Like that, here some calculation went wrong and so on, so steps like that, and we are avoiding the marks.
Okay, right. And but what did the mean the next semester? Would it be go in the same pattern?
At present, up to January 1st, it is there, sir, this semester. So next semester, we have to see what will happen. But we announced it will be online up
Hmm.
to January end or February. That's what we announced. Slowly, we are asking the research scholars to come
Okay, okay.
around. We are having about 750
Hmm.
research scholars now. So we asked about 250 research scholars to come to the campus. Just 3 days back only they came to campus.
Hmm.
So slowly we are asking them. And
So whoever are in the, I mean, the final year and trying to finish all their
yeah.
thesis
But for
work
some,
something.
the final year exam they will be completing by December 15th. So after that exams will be there. So after Pongal, we are asking them to come back to next semester starts at around January 15th or 16th. So by that time, at least we are asking them the finalists to come, and the MTech project people also should come. Those who have to complete the projects and everything. That's what we are planning for the time being.
Mm-hmm. Yeah, it's really a tough time to the world actually,
Yeah, yeah,
and now now again we are coming to know that the number of cases are again going up actually.
yeah. That's unfortunate. The second stage is started just now.
Yeah. Because today also we got the email from the actually the registrar
Hmm.
that this is the second wave of corona is also going to start actually.
Yes, yes, yes.
So
We
we
should
were
be.
hoping to things to the settle down, and now things are going up again.
Yeah, yeah. Earlier we used to give hostels with the sharing. That means twin sharing, something like that. Now we have to accommodate only one person in a room. Due to that, we want to. There is a limited accommodation also will be available. Even if we cannot call all the people in the campus also.
Right. Because the social distancing to
Yeah,
make the
social distance.
hygienic things and all things,
Yeah, yeah.
and actually a lot of care need to be taken care at personal ends also.
Yeah.
The students also need to take care the lot of thing at their end.
But whereas for the PG
So
people and the second year, third year, fourth year, there is no problem, sir. Only the first year only it's a challenging one for us, which we are
yeah,
going
actually
to start in next
for
month.
first year, yeah, first years actually जो है number of seats are drastically increased, and
Actually, it's due to
the,
EWS, sir. Due to EWS, 25%
yeah,
actually.
but